Welcome to today's class. This class we would be studying about your half adder and full adder. I've already given you some brief idea about different combinational what is the concept of combinational logic circuit. We're going to use that very concept and we will design half adder and full adder. Now what do you mean by this half adder full adder? These adder circuits are simply addition circuits or addition logics. They will add multiple binary bits. For example, what we have is the truth table for a 2-bit half adder. Let that be a 2-bit. Okay, this one is a 2-bit half adder, and this we're going to design a combinational circuit that will take on as x and y as input and give you the summation of these two input bits. Okay. Now in some cases we may have a carry, so that's why we also have another output, that is C. Now we tabulate all the possible combinations of two inputs. Let that be the two inputs are x and y, and for that we have 4 possible combinations. And for each possible combination we have a summation result and also a carry result. Only on the final combination we have a carry. Okay, if the two inputs are 1, then we're going to get the summation as 0 and a carry of 1. Okay, now we can use K-map to find the expression of sum and carry, or by looking at the table we can also directly define what should be the function such that the particular result comes in or particular input output combination comes in. Okay, so as I've already told you in the previous class, we can use K-map, and this is going to be a 2 variable K-map, and this is not practical to do a K-map for here because we are already have 2 inputs, so that is the simplest form. So I can directly say that the summation result is going to represent you an XOR gate here. Okay, that's very simple. There's going to be XOR of two inputs, that is x and y, and the carry you can say that is the AND operation of these two inputs. Okay, and I have also designed the logic circuit for that. XY is the input, we have XOR that gives you the summation, we have AND gate and that gives you the carry, because C is x dot y and S is x XOR y. Okay, so this is your half adder. It only adds two inputs. Okay, now suppose there is a case where we have to add 3 bits. Suppose for one calculation, like we have 1 0 1 1. For this bit calculation, the first bit calculation, we have 1 plus 1, that is 0, and there is a carry 1. So in this particular calculation we have to add 3 bits. So we have either we can use two half adders or we can use a full adder here. Okay, a full adder conceptually that is different only on the input basis. It has 3 inputs. X, Y are going to be your normal inputs, and Z we are going to consider that as a carry on the previous from the previous bit calculation. So for that we have simply listed out all the summation for each combination and also the carry for each combination. Okay, you can look for that by using the K-map. I have done here the K-map for the summation. You see there is no combination possible, there is no grouping possible, there are 4 individual minterms, so that's why the summation goes to something like this. Okay, the summation goes to something like this, and you can follow the same procedure for C, and there you will find some grouping and the expression is going to be something like this. Okay, I'm not doing that, that is going to be lengthy, and that is very simple to understand though, so you can do it for yourself. And the logic diagram for that is just like this, where you can say this is a 2-level implementation here. This is an AND and OR, again AND and OR. So you can say this is a 2-level implementation, but this is what the logic circuit is. Okay, so this is about your half adder and full adder. Okay, now let's get back to a final concept, is how to implement a full adder using multiple half adders. Okay, you see, when you are adding 3 bits, for example, for this particular example, when you are adding 3 bits, you have you have to add the first two bits x and y first. That will give you one summation S1 and one carry C1. Okay. After that, you have to add Z plus S1. Okay. Because the third bit is there, the carry bit is there. The summation from x and y is S1, and you have to add that with Z, that is the carry from the previous bit. That will give you your final result S, and also that may give you a carry. We're going to name that as C. Okay. So that S is here and C is here. So what you're going to do is you are doing two half adder operation. For x and y, there is an half adder operation that will give you S1, and for Z and S1 you are going to do another half adder operation, and I have done that on the expression, logical expression here. Okay, so first half adder for the final summation of a 3-bit addition, the first half adder operation is for x and y, and the second half adder operation is for Z and the summation from x and y. Okay, what about the carry? The carry you can find out like Z dot the summation S1 plus of C1. Okay, this will give you the final carry. I have compressed this into a simple expression, that is S1, because x y bar plus x bar y, that is x XOR y, and that is exactly S1. Okay, so on compact form you can write down the overall carry of a half adder operation can be written as like this, where Z is the carry for that particular bit calculation, S1 is the summation of first two bits, and C1 is the carry output from the first two bit calculation. Okay, so this is what the concept of implementing a full adder using two half adders. Okay.